Good morning. Welcome back to Physics 4C Lab. Today's lab, we are going to be looking at interference effects again. We looked at light interference a few weeks ago, several weeks back. Well, now we're going to go in and we're going to get some microwave sources, and that's what these are up here. So we have a microwave generator. And what we're going to be doing is, and here is a microwave receiver. And so I can't see the microwaves. My eyes aren't sensitive to that part of the spectrum. But what we're going to do is look at some interference effects. We've got some single slit and double slit devices here. Now, the microwaves are going to travel right through these pieces of plastic. But the plastic has copper that has been layered down on these pieces of plastic. So wherever the copper is, the microwaves should get absorbed. So, you know, when we first started talking about these interference effects, we said, well, there's a barrier. And so the copper, where the copper is present, is a barrier to the microwaves. And then that narrow region, those paths, the microwaves would not be stopped. So if I think of individual microwave photons, the way we represent those is with wave functions. And the wave function for even an individual photon is spreading out. And in order to predict where that photon is going to end up, we have to follow all possible paths. And so this barrier says, well, all these paths surrounding this slit lead to the microwave being absorbed. That photon gets absorbed. There are some paths where the photon doesn't get absorbed, and so it can continue on. And what we've been learning in quantum mechanics is when you reach a certain point, if there's a narrow set of paths available to a particle, much, well, kind of the size of their wavelength, for example, that you'll see significant spreading. So the paths that are possible once the microwaves come outside of these slits, those paths begin to spread out again. And that's where we pick up interference effects. So there's an interference effect from the one slit, and then interference effects from two slits. Okay, so let's see what we got on the board here. So name of the lab, microwave interference. The objective is to be able to come in here and measure the intensity of the interference pattern for microwaves for single and double slit. So the idea is we want to see the interference pattern. So if we start with a microwave source, a generator, let's say that we go with the single slit. So what I can do now is I can place a single slit barrier in the path of the microwave photons as they come out. Then what we can do is we can take the receiver. Now, the receiver is reading pretty high when it's here in the center. But what we can do is we can rotate the receiver outwards. Now, in class, we've been talking about flat screens versus circular screens. And in this case, we don't want to pick up the distance effect that a flat screen would produce. So what we do want to do, and when we've got equipment that will allow us to do this pretty easily, is we want to maintain the same distance and just be able to see the angular effect. So as we move to different angles with this receiver, what's the interference pattern going to look like? So that's the idea here. Now, so a couple of things we got to get measured right up front. We got to measure the width of the single slit, and then we got to measure the width of the double slit. Now, both of these are going to give us diffraction effects, right? Both of these slits are finite in size, and so we are going to see a diffraction effect here, entirely diffraction. In this case, we'll see a diffraction envelope with two slit effect inside the diffraction envelope. So we'll see both sorts of things going on. Now, we need to measure the slit width here, so we'll get the width here. And then with the double slit, we need to get the slit width and the center to center distance between those two slits. So let's see. I got out my ruler, and I've got my single slit here, so I'm going to measure this width. And the width came in at 2.5 centimeters. So that's what I'm going to use for A for this single slit. Now, when I took a look at the two slits, what I noticed was that the slits are different. In width, they're not the 2.5. This slit width is at 3.2. Now, that presents a problem because when I go over to the other slit, it's 3.4. So I got a 3.2 centimeter slit and a 3.4. One way we could get around that is we could get some aluminum foil. So I got some aluminum foil and I narrowed one of the slits so that they now both measure 3.2. So now, yep. So now what we've got is we've got two slits, both at 3.2 centimeters. And now what I can also do is I got to measure center to center. Now, there are little marks right here that were made at the centers. And so measuring between these, I ended up with 5.6. Okay, so those are the numbers we'll go with. Now, also what we would like to have, I guess, if we're putting together kind of a theoretical prediction here of what effects we might see, we need to have something on the wavelength. Now, with these microwave generators, there's a couple different approaches here. We could go in and we can check the wavelengths ourselves, and we'll do that. So we will go in and look for the n equal 1/2 0 points and get some angles and use those to come up with some of our own measurements of what it looks like the wavelength might be. Also, the manufacturers give us a couple of wavelength values. If I look at the generator itself, it says that it's 3.0 centimeters. If I look in the instruction manuals, it says it's 2.85. So maybe we do need to go in and check and see which it might be. In any case, I'm going to go with the 2.85. That looked like more of a serious number. That was inside the instruction manual, and it had a list of all of the specifications. So I'm going to say the accepted value for the wavelength is 2.85 centimeters. Okay, so that's the microwave source. That's the wavelength for those photons. Now, just a reminder from class, so if we have a single slit, the interference pattern we're predicting, or the intensity pattern for the interference, is going to be a sine squared n pi over n pi, where n is defined through this equation. It's a sine theta. Who wrote? Wait, let me get rid of these pi's. Okay. Good thing we saw that. Those should be wavelengths. So let me get that changed. It's all Greek, right? So one Greek letter is as good as another. So this has got to be wavelength. So it's some number of wavelengths is equal to a times sine theta. And we've talked about this formula and derived it in class. When we get over to the double slit, we're going to have a formula keeping track of the diffraction effect, and we're going to have a formula keeping track of the two slit effect. So both effects will be ongoing. This is what the single slit all by itself we're predicting it will look like. Remember, we're going to do a circular screen maintaining a fixed distance. So if we do that, our prediction is that we should get an intensity pattern that's following this formula. Now, if you take a look, I think the A value here we decided was 2.50, but the wavelength is bigger than the slit. And in cases where the wavelength is bigger than the slit, we're going to hit 90 degrees, maybe somewhere in here. So there's going to be a cutoff. So when we hit 90 degrees, That's going to be it. It says that the entire diffraction interference pattern from plus 90 to minus 90, or from 90 degrees in one direction, 90 degrees in the other direction, that entire interference pattern is only going to include this portion of the central maximum. So we're not even going to see these. We're not even going to see these n equals 1, these zeros. We're not going to see the zeros. We're not expecting to see the zeros. So what we would predict then, we're going to see, is if I set this up, so I'm going to set up my receiver. There's actually a sensitivity measurement on this, so I can turn this up. The receiver reading goes from 0 to 50 units of intensity. And so what I can do, or what I'm going to do, is I'm going to adjust the sensitivity till it's right on 50 in the middle. And so what that would do for us in our formula, we're going to say that the I naught is equal to 50 intensity units. Now, these receivers are not calibrated, so it just has a scale with a bunch of numbers on it. We don't know exactly, we don't know how many watts per square meter that is, and so we're just going to call them intensity units. So 50 intensity units is what we're going to max out at. And then what we can do, I got to get the slit in place. Let's see, here is the single slit. So we're going to measure distances from here. I can slide this probably a little closer. We're going to measure distances from here out to here, and we want that to stay constant. So we'll see how we do that with the setup. It's got a fixed bar that rotates and enables us to do that pretty easily. So I'm going to, do a series of measurements. Maybe every 5 degrees or so, we'll do a measurement and see how the intensity is dropping off. It's not such a complicated function here. The function is pretty straightforward. And so as I'm going from side to side, I can see on the scale here, as I rotate this over from side to side, the intensity drops down. And what we want to do is check and see, is the drop-off following the theoretical prediction? So we're just checking to see if reality matches up with what we've been learning in the textbooks. All right. So here's maybe what our data table is going to look like. So I'll say this is a single slit. Now we're going to have more than this one data table. We'll have one for single slit and we'll have one for the double slit. But for the single slit, what we can do is come down about every 5 degrees, and then based on these formulas, we should be able, now I've got this listed as M, but this could just as easily be N, depending on which effect we're looking at. Those are keeping track of the same thing here. And so what we can do is we can calculate these values, and then we'll find out what the intensity is. So, and then we can come back on these intensity plots. So what we're keeping track of here is intensity is in the vertical direction here. And so what we can do on the graph is we can measure over to these different values of N or M, and we can plot it. We'll plot these values and say, are they lining up with our prediction, or are they not? Okay. So we'll get, what we'll have is we'll have a theoretical curve. So the theoretical, and I've drawn these. So I'm going to provide these. So I went online and I have a function generator or function grapher that I go to. And this is what it's predicting for the single slit case. And then here's what it's predicting for the double slit case. So I'll put these in the slides. You guys will have access to these plots. and then you can put those into your lab reports, and you can plot your measurements onto these graphs. And we'll see how it compares. So, so yeah, maybe this is what it looks like. Here's one of those graphs, and now here is a data table, and then here are measurements of you know, what we actually went in and measured. So now, if for the single slit, what kind of information, what things are we learning here? And for the single slit, if our measurements match up with a kind of a theoretical curve, that might suggest to us that the wavelength number that we're using, the 2.85, is reliable. But if we find out that, let's say that our data is more narrow, well, maybe the wavelength that we're looking at is the 2.85 is not reliable. That would enable us to go in and get a different value for the wavelength. Okay. So if the wavelength's bigger, we expect that the pattern's going to be spread out more. If the wavelength is smaller, we're expecting the wave pattern won't be spread out quite so much. Okay, we'll see. We'll see if that's the effect. Maybe we will have evidence that the wavelength is something other than what the manufacturer was telling us. Okay, so we can make comments on this. Now, this is more complicated, right? There's a lot more stuff going on with this two slits than there is with the single slit. So let's take a look and see. First of all, in class, in lecture, what we've shown is that when we have two slits, each slit with a finite width, there is a diffraction envelope, and then there is a two-slit effect going on within that diffraction envelope. And that complicates the functions. So we can certainly say that, you know, at these zero locations, where the intensity is, we're predicting it would drop right to zero, that is where the effects from the two separate slits are going to be canceling each other out exactly. Now, built into the formulas that we have here are assumptions. I don't know if you guys remember this, but in lecture we were talking about the assumptions that we make for these interference formulas is that we're, in terms of distance, the distance from the source out to where we're making the measurement, or I'm sorry, from the barrier out to where we're making the measurement, in order for these formulas to be reliable, they need, this distance needs to be fairly large compared with the size of the slit and compared with the wavelength. Now, we're going to do the best we can to make that work. You know, the wavelengths we're looking at are a few centimeters. The slits also are several centimeters in width. The distance between the two slits is, you know, more. It's like 5.6. And the distance out to where we're going to be making the measurements is like 60 or 70 centimeters. So we're doing okay with that. So we're, you know, our receiver is far enough out that it's roughly following the approximation that we're using, which is saying once we get far enough away, these are the formulas we're going to end up with. And then the other question comes up with, do we have ideal generators and ideal receivers? So if you notice, on the front of these, there are these horns, which also complicate the measurements that we're making. So in any case, we'll see. I think what we're going to find probably is that kind of qualitatively, the measurements are going to match up reasonably well. We'll see if whether or not this is fairly precise, or whether there's a lot of uncertainty in some of the measurements. Anyway, for the double slit, this becomes a little more complicated, because if we're doing every 5 degrees, the question becomes whether or not we're getting enough samples to see the intensity come down and back up. So what we might have to do for the double slit case is actually do a series of measurements and pick different angles. I would like to get that angle right there. So I would like to get the angle where it where it zeroes out. And then I would like to get this angle too if there's another peak. So some of these prominent locations, so maybe get several measurements on the way down, make sure we get this one, a few measurements up to this next peak on the way down. Now, I think we mentioned, maybe I didn't mention, that when you go to the double slit case, the widths are different. We didn't mention that. So this worked out to be 3.2 centimeters, and I think this one was 5.6. I'm going to write that in. So now that's bigger than the wavelength that we're working with. So we're assuming 2.85 centimeters. And now these widths are bigger. And so if we get to a bigger width, that says that at 90 degrees, we are going to be able to include the entire central maximum. So the entire central maximum now, theoretically at least, we're predicting, should land within that 90-degree measurement. Okay. So now the prediction from these graphs also, and I should point this out, if you take a look at these theoretical graphs, it really flattens out. So it turns out, even with a two-slit maximum, an n equals 2 out in this region somewhere, that maximum's getting flattened out by the diffraction curve. So this is predicting that we're going to, as we get out to the, probably well before 90 degrees, if we get out to 75, 80, 85 degrees, this is predicting we might not see any intensity at all. So if we do see something, we'll have to try and think what could be causing that. All right. But anyway, that's the idea. So single slit, pretty straightforward. We'll do every 5 degrees. Double slit, we're going to pick our angles more carefully and try and pick up some of these prominent points along the way. All right. And then also we can check wavelengths. One easy place, relatively easy, would be to look for the n equals 1/2. Now at n equals 1/2, we're predicting the intensity goes right to 0. So what we could do is just find the angle at which we go to 0, and then using that theta value and the m value, that's enough information. We could go in, and the widths and the d values, that's enough information. We should be able to go in and determine what the wavelength is. Okay, so we'll get our own independent wavelength. All right, I think that's everything we wanted to cover here at the front of the class to get started. So now let's do some close-ups. Let's go back and look at the setup. I've got the setup just right back here, and see what some of these measurements are going to look like. So here we are. I'm kind of in the middle of these single slit measurements. I thought it might be a good time to show you what I've been up to here. So I started out at 0 degrees with the receiver right out in front of the transmitter. But now I'm out to about 60, 65 degrees. And so the setup looks like this. I had mentioned that there are these metal support rods that rotate around a center point, and you can see that the this should look like the homework problems we've been looking at. There is the barrier and the angle. So if I get something coming straight out here, the angle that we're measuring is this angle inside here. Now, I started to collect the data here. You can see my data tables that are coming together. And so what I'm doing is I'm writing down the intensities. It turned out that even at 0 degrees, I wasn't able to get the intensity up to 50. In fact, I was only able to get it up to 20. And I decided that rather than reduce the distance
out to the receiver. I could bring the receiver in and have the intensity go up. I decided that I would stay with the receiver at a pretty good distance. So I think the receiver is set out at 40 centimeters. So some combination of bringing the receiver in a little closer and then turning up the intensity as best I could in order to get these measurements. So again, the I naught, at least for this single slit set of measurements, is going to be 20. So you can see here's what the receiver is reading. The receiver right now is reading about 2 or 3 intensity units, and we're out at 60 degrees. So we'll see how that matches up with the theoretical predictions. Now, another thing I guess I should point out here is I put up an aluminum shield here to block any of the signal from coming around the single slit. I wasn't sure how close to put the single slit to the horn on the microwave, so I decided what I would do is build an aluminum barrier. And so the idea is no paths are coming out from the side, and so everything that's reaching the receiver, I'm hoping, is going through that single slit that we have open. I'm going to finish up this side, and then I'm going to do the other side. So I'm going to do from 0 to 90 on this side at 5-degree intervals, and then I'll switch over and pick up this other direction, and I'll put the data tables into the information for the lab. So watch for those. So just a quick wrap up with the single slit. So we're still on single slit. We still have that aluminum piece on the side as part of a barrier. I just wanted to report that when I went back in this other direction, not necessarily symmetric. There were some significant differences in the numbers that I was reading, and I've kind of gone back and forth, and I'm finding that the numbers are not necessarily exactly reproducible. There is some variance just going back and forth and doing the, and that is kind of what happens with these microwave experiments. We've got this experiment, we have another microwave experiment coming up with polarization where we'll get the microwave generators back out again. I hope it's not a traumatic experience. But in any case, you'll see with the data tables that I'm going to be posting that not necessarily as much symmetry as we might have predicted. All right, well now I'm set up with the 2 slits. I've gone back, I've got a more carefully measured out slit width on that right side. I added that aluminum foil. And so now the widths match up 3.2 centimeters on each side. I've got everything anchored down, so that's what we were doing before with the single slits also. So I don't want motion here. I want it to be able to rotate freely around that axis right below the barrier. Now here's the receiver, and if you look also, I put some vertical supports to align them as best possible. So I've tried to configure this. And then the last thing maybe I can mention here, I've got my data table ready to go here. I've got this set out at every 5 degrees right now, but I'm expecting along the way I'm going to additionally add in those angles at which we hit the zeros and where we hit the peaks. So any of those, I'm going to include those in the data table. And then, interesting, with the 2-slit configuration, I was able to get to an intensity of 40 when we are at 0 degrees. And so maybe we'll have a larger scale to work with. There's the angular scale, just so you guys can see that. All right, I am going to start taking measurements. Okay, so I'm just finishing up the measurements using the 2-slit setup, and I'm kind of going back and forth, and kind of like I saw with the single slit, I'm not seeing as much symmetry as I would have expected. I'm seeing some variation, so I'm kind of going back and forth. I'm slowing down to get those zeros and the peaks, or the minimum and the maxima along the way, so we can get those independent wavelength measurements. Anyway, I'm expecting I'll just, I'll wrap this up here in a bit. I've got a few more measurements to make. There's a lot of up and downs following these peaks, through the 0 to 50 degrees out, and then things just tend to taper off. We'll see if that's what happens here. But again, I think this will be I think I'll just be wrapping this up with a few more measurements.